Welcome to G Fun Facts Online. For decades, humanity has been staring at a massive, untapped battery. 80% of the world's offshore wind resources are locked away in ocean waters far too deep for traditional wind turbines. You cannot hammer a steel monopile into a seabed that is 1,000 meters down. But as we stand here in early 2026, the global energy sector has crossed a watershed moment. Floating offshore wind has officially graduated from a promising, slightly crazy engineering curiosity into an industrial reality. The days of tiny one-off prototypes are over. We are now in a world of record-breaking gigawatt auctions, fierce geopolitical races, and mind-bending technological breakthroughs. Today, we are taking a deep dive into the state of floating offshore wind platforms in 2026, exploring how engineers are conquering the deep ocean, not to plunder its resources, but to harvest its boundless energy. Let us start with the hardware, because the technological renaissance happening right now is fascinating. A floating wind turbine is no longer just a steel structure bobbing in the water. It is a highly sophisticated integration of hydrodynamics, aerodynamics, and digital intelligence. For years, the industry debated over which substructure would win. Would it be spar buoys, semi-submersibles, or tension leg platforms? In 2026, the answer is hybridization. Semi-submersibles remain the workhorses because of their shallow draft. You can assemble the whole turbine at the port and tow it out, avoiding the incredibly dangerous and expensive process of lifting massive blades out in the treacherous open ocean. But engineers have realized that one size does not fit all. Take Japan's Go-To floating wind farm, which just began commercial operations in January 2026. To survive the brutal typhoon-strength winds of the Pacific, engineers designed a revolutionary hybrid spar-type floater. They used a steel upper section combined with a pre-stressed concrete lower section. This brilliant move drastically lowered the center of gravity, while slashing material costs. Speaking of concrete, we are seeing a massive shift away from pure steel. The volatility of global steel prices has pushed developers to rethink their materials. Recent lifecycle assessments show that using concrete floaters can reduce the carbon footprint of a platform by 40 to 50% compared to all steel equivalents. Plus, you can mix and pour concrete locally, stimulating local economies and bypassing the heavily bottlenecked shipyards in Asia. Meanwhile, tension leg platforms, or TLPs, are making a huge comeback. These platforms are tethered to the seabed by taut tendons that virtually eliminate vertical motion, making the turbine incredibly stable. The historical problem with TLPs was that installing them was a nightmare, but new suction anchor innovations have solved this, making TLPs a top contender for the ultra-deep waters of the Mediterranean and the United States West Coast. Now, keeping these massive structures from floating away brings us to the next big breakthrough: mooring and anchoring. Imagine a traditional floating wind farm with 100 turbines. In the past, each turbine needed 3 to 4 anchors. That meant cluttering the seabed with nearly 400 massive anchors, driving up costs and causing significant environmental impact. The solution we are seeing rolled out commercially in 2026 is shared anchoring systems. Projects like Deep Farm have proven that multiple turbines can share a single anchor point without compromising the stability of the grid. This cuts the number of required anchors by up to 50%, drastically reducing capital expenditures and minimizing the footprint on the ocean floor. And the mooring lines themselves are getting a high-tech upgrade. In February 2026, Dublin Offshore received certification for their new load reduction device. This is a passive system that sits directly within the mooring line. It uses buoyancy and ballast to absorb and dampen the violent snatch loads caused by rogue waves. Because this device absorbs the shock, developers no longer have to use incredibly heavy and expensive steel chains. Instead, they can use lighter, cheaper synthetic ropes made of nylon or polyester. But anchoring the turbine is only half the battle. You still have to get the electricity back to land. Connecting a moving giant to a static grid is an immense engineering challenge. Remember, a floating turbine does not just sit there. It heaves, sways, and surges with the ocean. The power cable connecting it needs to survive millions of bending cycles over a 25-year lifespan without snapping. This year, companies like Nexans achieved a critical milestone by qualifying 145 kilovolt dynamic inter-array cables for water depths exceeding 1,000 meters. These umbilicals are reinforced with double armored layers and highly fatigue-resistant cores. This technology is the literal key that unlocks the deep waters of the Atlantic and the Asia-Pacific regions. So the technology is ready, but what does the global market look like? Over the last 12 months, the center of gravity for floating wind has shifted dramatically to the Asia-Pacific region. South Korea is the undisputed star of 2026. They just announced a landmark auction result, where Equinor's Firefly project was awarded a long-term contract. At 750 megawatts, Firefly is the world's largest commercial-scale floating wind project to secure a route to market. Located 70 kilometers off the coast of Ulsan, it is the blueprint for gigawatt-scale deployment, proving floating wind can compete in highly industrialized markets. China is also moving at incredible speed, deploying demonstration projects in the South China Sea. Their Yangtze West Shapa project is testing typhoon-resistant turbines in shallow waters between 30 and 50 meters deep, a segment European developers have largely ignored. Japan is doubling down too, focusing heavily on localizing the supply chain and using floating wind assembly to revitalize its legendary shipbuilding industry. Over in Europe, the region is proving to be the comeback kid. After a disastrous auction round in the UK where no offshore wind was bid, the government roared back in January 2026 with allocation round 7. They awarded a record 8.4 gigawatts of total offshore capacity, and crucially, this included contracts for 2 massive floating wind projects, Erebus in the Celtic Sea and Pentland in Scotland. The strike price for these floating projects cleared at roughly £216 per megawatt hour in today's money. Yes, that is high compared to traditional fixed bottom wind, but this price reflects the first mover premium necessary to kickstart the supply chain. It is a strategic investment by the UK to regain global leadership. Meanwhile, France is pushing forward with its Pennevel project in Brittany, and European leaders just committed to a staggering 300 gigawatt offshore target by 2050, relying heavily on floating wind for the deep Atlantic coast. But the story is very different in the United States, which is currently navigating a massive policy shock. The passage of the One Big Beautiful Bill Act, or OBBBA, in July 2025 fundamentally altered the playing field. The act rolled back many previous subsidies and imposed strict domestic content requirements, mandating that up to 35% of the project components be made in America by 2026. Because the U.S. domestic supply chain for floating platforms is still nascent, this has created a massive short-term bottleneck. However, the same act also forced the Bureau of Ocean Energy Management to hold regular offshore lease sales in the Gulf of Mexico, the Gulf of Maine, and Oregon. To survive this turbulence, developers are pivoting away from the federal government and relying on state-level procurement. States like California and Maine are aggressively using state mandates to backstop the federal uncertainty, creating a bifurcated market where federal momentum is slow, but state-level action is intense. This brings us to the ultimate question: the economic equation. The levelized cost of energy, or LCOE, is the single most important metric. Let us face the hard truth. As of early 2026, floating wind remains expensive. Floating wind sits between $150 and $220 per megawatt hour. Fixed bottom wind is between $70 and $100. Gas and nuclear hover around $120 to $150 in volatile markets. So floating wind is still pricier than fixed wind, but it is actually becoming highly competitive with new nuclear and peak gas generation in regions with high energy prices. To get the cost down to the industry target of $60 per megawatt hour by 2035, developers are embracing massive modularization. They are moving away from bespoke, custom-built platforms and moving toward mass-produced kits that can be assembled by local labor. But the ultimate bottleneck right now is port infrastructure. You cannot assemble 50 massive concrete floaters without hundreds of acres of quayside laydown area. Governments are pouring billions into port upgrades right now to create gigafactories of the sea. But perhaps the most exciting part of this 2026 reset is how these platforms are integrating with the environment. The floating wind farm of 2026 is not just a power plant. It is an integrated marine ecosystem. We are seeing co-location of food and fuel. For example, why send electricity back to shore when you can make fuel right on the ocean? The HOPE project is scaling up offshore electrolysis, aiming to pipe green hydrogen directly from floating turbines to shore, bypassing the electrical grid entirely. This is a massive game changer for wind assets stranded far out at sea. We are also seeing aquaculture fully integrated into wind farms. The ULT FARMS project is running active pilots across the North and Baltic Seas, cultivating mussels, oysters, and seaweed right between the turbines. In Sweden's Mareld wind farm, they have partnered with a company called Subfarm to install autonomous fish cages between the turbine rows. These cages can be submerged 70 meters deep to avoid storm damage and then brought to the surface for harvesting. This protein and power model creates an artificial reef that boosts local biodiversity. And the industry is moving beyond just doing no harm. They are actively doing good. To protect the seabed, projects like Ocean in Scotland are using fleets of autonomous underwater vehicles to map hundreds of kilometers of the ocean floor, ensuring that anchors completely avoid sensitive coral and spawning grounds. They are even using new distributed acoustic sensing technology on their export cables. This literally turns the subsea power cable into a massive fiber optic microphone capable of detecting the vocalizations of baleen whales tens of kilometers away. This real-time data allows operators to pause any noisy maintenance activities the moment endangered species swim into the area. As we look toward the 2030 horizon, the trajectory is crystal clear. The reset of 2025 and 2026 cleared the hype from the market and replaced it with steel and concrete. We are heading toward a future of 20 megawatt turbines with rotor diameters exceeding 300 meters. We are building artificial energy islands in the North Sea that will collect power from gigawatts of floating wind and distribute it to multiple countries simultaneously. The floating offshore wind platform is a testament to human ingenuity. With projects like Firefly lighting the way in Korea, Pentland surging in Scotland, and the Gulf auctions looming in America, the era of floating wind has truly begun. The water is deep, the winds are strong, and the anchors are holding fast. Thanks for tuning in to G Fun Facts Online. Keep exploring, and we will see you next time.